Welcome to part 3 of our snow science module. I am Mike Levis, one of the avalanche instructors with Mount Hood Ski Patrol. In the first 2 parts of the snow science module, we discussed the parameters that drive snow crystal formation, temperature gradient, temperature, and snow density, and the metamorphic processes that drive the evolution of the snowpack structure. In this section, we will discuss other physical processes that drive the structure of the snowpack. In particular, we will focus on near-surface processes that can create facets and weak layers in the top 10 centimeters of the snowpack. These near-surface weak layers can evolve into deep buried weak layers as more snow falls on the surface and the snowpack deepens. Keep in mind as we go through this that these are not isolated processes. All of these processes are going on all the time in the snowpack. One process may dominate based on the specific environmental conditions at a specific moment. So armed with this knowledge of the big knobs driving crystal formation, let's take a tour through the snowpack. As this slide shows, to have conditions in the snowpack for an avalanche, you must have a slab, that is something to slide, a weak layer, something to fail, and a bed surface, something to slide on. The snowpack is made up of a layered structure that reflects the weather history over the course of the season. The key weather parameters of interest are precipitation, type, rate, and amount; temperature, highs and lows; wind, length, strength, direction, and duration. These weather factors determine the cohesion of the snow, that is the bonding within a layer, as well as the adhesion of the snow, that is the bonding between layers. This is important to us in assessing snowpack stability, since all the action will occur at the interface between layers. For example, large grain size differences will result in poor adhesion between layers. Weak layers will typically be composed of faceted crystals, such as depth hoar or buried surface hoar. Very strong layers, such as ice, can act as a bed surface for consolidated layers to slide on. In addition to the metamorphic processes we discussed in the previous section, there are other physical processes at work in the snowpack. Gravity acts on the snowpack and will both compress the snow and provide a force acting downslope. Friction will affect the snowpack, both at the interface between snow layers and in places where the snow contacts the other objects, for example, a rock. And of course, over time, all of these processes are cumulative. Let's focus on gravity and the effect it has on snowpack structure and stability. Gravity is a force that is proportional to mass and always acts toward the center of the Earth. Gravitational force can be decomposed into a force parallel to the surface of the snow and perpendicular to the surface of the snow. Friction is a force that opposes the component of gravitational force parallel to the surface of the snow. Take a moment to study the diagram on the slide and make sure you're clear on these concepts. The gravitational force on the snowpack and on the corresponding frictional force result in 2 distinct effects: glide and creep, shown on this slide. Glide is the uniform movement of the entire snowpack down the hill due to gravity. Creep is the downslope movement of snow, also under the influence of gravity and affected by the friction at the interface between a consolidated layer and a bed surface. Glide and creep occur simultaneously and are additive. The result is that the movement of the snowpack downslope with different velocities through the depth of the snowpack. Layers close to the bed surface are slowed by friction, while layers closer to the surface move at a higher speed. This difference in velocity introduces stresses in the snowpack. Another gravitational force on the snowpack is settlement. This effect comes from the effect of gravity over time and results in the slow densification and compression of the snowpack. We see this on Mount Hood a lot around trees, where settlement cones show the magnitude of settlement at that time. Let's move on and discuss what is probably the most important near-surface process of interest to us. This is radiative heating and cooling due to the energy exchange at the snow-air interface. First, let's review some basics. Radiated energy occurs over the entire frequency spectrum and includes radio waves, infrared, visible light, ultraviolet, all the way up to gamma rays. The higher the frequency, the higher the energy of the emissions. Visible light occurs over a relatively small portion of the spectrum, shown in the center of the graphic on this slide. All things above absolute zero absorb and emit radiation. You emit and absorb radiation. The chair you're sitting on emits and absorbs radiation. More importantly, snow, rocks, and trees all absorb and emit radiation. For the purposes of our discussion, the sun emits shortwave radiation and the earth low frequency, long wave radiation. The combination of these long wave and short wave effects will affect the snow surface temperature. Energy absorption will heat the snow, and energy emission will cool the snow. As we discuss near-surface processes, we will think in terms of radiation balance. Radiation balance is simply the radiation absorbed by the snowpack less the radiation given off. Positive radiation balance will heat up the snow surface, causing surface melting. Negative radiation balance will cool the snow surface and result in freezing. Note when I refer to the snow surface here, I'm really referring to the top 10 centimeters or so of the snowpack, since the radiation effects occur to about that depth. Since radiation is energy, as you may remember from your physics classes, it cannot be destroyed, but can only be converted to other forms of energy, such as heat. When shortwave radiation from sunlight hits the snow surface, most of it is reflected. Only a small portion is actually absorbed by the snow. In addition to shortwave radiation from the sun, the snow itself and other nearby objects emit long-wave radiation, shown as the L in and L out on this slide. During daylight hours, the shortwave radiation from the sun is much greater than the long-wave radiation emitted by the snow. The radiation balance is positive, so the net effect is the temperature of the snowpack surface layer increases. At night, without the shortwave radiation, the long-wave radiation emitted by the snowpack dominates. The radiation balance is negative, and the snowpack temperature drops. In real life, the situation is more complex. Radiation is absorbed and reflected by clouds, water droplets, just about everything. On a cloudy day, the sunlight will be reflected by the clouds, and the amount of shortwave radiation impacting the snowpack is reduced. The material in the clouds emits long-wave radiation, some of which goes out in the atmosphere and some of which impacts the snow surface. Some of the long-wave radiation emitted by the snowpack is reflected by the clouds back into the snowpack. So the situation can be complex. However, the radiation balance principle still applies. Positive radiation balance heats up the snow, negative radiation balance cools the snow. So let's consider a couple of concrete examples. Consider the case where we have clear skies. During the day, the sun will heat up the surface layer, and at night, long-wave radiation emissions will cool the surface. With the emissions of long-wave radiation at night, the cooling effect on the snow can actually bring the snow surface temperature down below the air temperature. The top layer of snow is colder than the surrounding air, increasing the surface temperature gradient. As the graphic on the right indicates, there can be a big temperature swing on the surface of the snowpack. This will result in large temperature gradient in the upper layers of the snowpack near the surface. If the snow is too dense, this will result in this will result in near surface faceted crystals forming in the surface layer of the snowpack. This slide shows a picture of the near surface recrystallization described in the previous slide. The surface of the snow melted due to the heating effects of the sun, then refroze at night when the long-wave radiation emissions cooled the surface. Below the surface crust, faceted snow formed due to the large temperature gradient created in the top layer. Another potential result of cold, clear nights is surface hoar, shown on this slide. Recall that in the previous section, we referred to surface hoar as frozen dew. This will occur when there is sufficient moisture in the air to form crystals and when there is no wind to scatter the crystals. The second case we'll discuss is wet layer recrystallization, shown in this slide. This case occurs when there is a layer of wet snow with high water content on the surface of the snow. This typically occurs due to surface layer melting or rain events. This wet layer freezes as temperature drops and forms an ice layer. New low-density snow is then deposited over the ice layer. The ice layer does two things. It can act as a bed surface for layers above the ice to slide on, and it acts as a vapor barrier and creates a high temperature gradient layer that results in faceted crystals forming on layers around the ice layer. This slide shows examples of crusts on snow created by wet layer recrystallization. All of these crusts create vapor barriers resulting in high temperature gradients and potential buried weak layers. So that brings us to the end of part 3 of our snowpack discussion. We have discussed the effect of gravity and the key role radiation balance can have in near surface effects. In our final module in snow science, we will discuss trigger mechanisms and how the crystal types and snow structures we have been discussing can result in avalanche initiation.